All right, welcome to the Explainer. Today, we are diving deep into something absolutely critical in the world of AI, reinforcement learning from human feedback, or RLHF. This is the process, the secret sauce, really, that takes a large language model from just being a raw next word predicting machine and turns it into a genuinely helpful and coherent assistant. So, here's the plan. We're going to start with the big why, the whole AI alignment problem. Then we'll walk step by step through the classic three-stage RLHF process. After that, we'll look at where things are headed with a much slicker approach called direct preference optimization. Sound good? Let's jump in. Okay, first things first. Let's really nail down the core problem that RLHF is even trying to solve. I mean, why can't we just take these huge pre-trained models and use them straight out of the box? What's the issue? Well, the thing is, these base models are trained on a pretty simple but massive objective. Just predict the next word. That's it. They've read a huge chunk of the internet, and their whole world is about figuring out which word is statistically most likely to come next. But that doesn't teach them to be helpful or harmless or honest. Their goal isn't to satisfy you, the user, it's just to find the most probable sequence of words. And those are two very, very different things. And this leads to all sorts of problems, right? You get models that just make stuff up, what we call hallucination, and they do it with total confidence. They can spit out biases they learn from their training data, completely ignore your instructions, or even generate stuff that's flat out unsafe. All of this makes them totally unreliable, and frankly, a bit dangerous to use in the real world. So how do we fix this? Well, here's the interesting part. The very first step in this whole alignment process, it isn't actually reinforcement learning at all. Nope, it's more like we're sending the model to a finishing school first to give it a much better starting point before we get to the really complex stuff. This step is called supervised fine-tuning, or SFT for short. The idea is pretty simple. We take that huge base model and we keep training it, but we switch up the data. Instead of the whole messy internet, we use a small, pristine, super high-quality dataset. This dataset is full of perfect examples, prompts followed by fantastic human-written answers that basically show the model, hey, this is the style we want. This is the format we're looking for. And this is absolutely key. This newly fine-tuned model becomes our reference policy. We'll call it PI-SFT. Now, in the world of reinforcement learning, a policy is just a fancy word for the model's strategy. You know, how it decides what to generate. So this SFT policy is our new and improved starting point. It already knows the basics of how to have a good conversation, which makes it way more prepared for the next, much trickier phase. Okay, but just showing the model what a good answer looks like isn't quite enough. It knows the style, but it doesn't really understand why one answer is better than another. We need to teach it to distinguish good from bad. And this is where the human feedback part of RLHF really kicks in. We're going to build an AI preference judge. So here's how we do it. We take a prompt and we let our SFT model, the one we just trained, come up with a few different answers. Let's say 4 or 5 of them. Then we take those answers and we show them to actual humans. Their job is simple. Just rank them. This one's the best, this one's second best, and so on. By doing this over and over, we end up with this fantastic data set made of comparisons. For any 2 answers to the same question, we now know which one a person liked more. Now, we take all that human ranking data and we use it to train a brand new model. This one is called the reward model. And you can think of it exactly like an automated preference judge. Its entire purpose in life is to look at a prompt and a response and then spit out a single number, a score, that predicts how much a human would probably like that response. So how do you train a model to do that? Well, this is where it gets really clever. We don't try to teach it to predict an absolute score, like this answer is a 7 out of 10. That's way too hard and subjective. Instead, we just teach it to answer a much simpler question. Which of these 2 is better? The math behind this comes from a neat statistical idea called the Bradley-Terry model, which was designed to predict who would win a match between 2 players. For us, the players are just 2 different answers from our AI. And the training goal here is really simple, but it's super powerful. If you look at the formula, all it's trying to do is make sure that the reward score for the winning response, the one the human liked, is higher than the score for the losing response. The whole point of this loss function is to maximize the gap between those 2 scores. So anytime the model gets it wrong and accidentally gives the loser a higher score, the loss function basically gives it a penalty and nudges it to fix its internal logic. You do this thousands and thousands of times, and the model starts to build a really solid intuition for what humans prefer. Okay, quick recap. We have our SFT model that knows how to talk coherently, and now we have our reward model that acts as our automated preference judge. It's time for the main event. We can finally bring in reinforcement learning to put these two pieces together and actively steer our model toward better answers. The algorithm for this is called proximal policy optimization, or PPO. Now, the objective function you see here, yeah, it looks a little intimidating, but I promise what it represents is actually a really beautiful balancing act. This formula is the absolute heart of the entire RLHF process. See, it's basically a tug of war between two different goals. The first part, that R5, that's the reward. This pushes our model to generate answers that our judge will love, to get the highest score possible. But the second part of the equation acts like a leash. It's something called a KL divergence penalty. And all that is really is a way to measure how much our new model has changed from our original SFT model. It's a penalty that says, hey, go get that reward, but don't get too weird. Don't forget how to speak normal, coherent English. And honestly, this is what makes the whole thing work. This KL penalty is the secret sauce. Without it, the model would just find weird ways to cheat the system. We call it reward hacking. It might figure out that for some bizarre reason, the reward model gives a huge score to answers that just repeat the word awesome 100 times. The KL penalty is the anchor that stops that from happening. It keeps the model grounded in reality and forces it to generate language that's actually sane and useful. So this whole three-stage pipeline, SFT, reward model, then RL, it definitely works. But man, it's complicated, right? You're juggling multiple models, and that RL training loop can be super unstable and a real pain to tune. It's a bit of a beast to manage. And that complexity got researchers thinking there has to be a better way. And the big question they started asking was this: can we do this more directly? Can we optimize for human preference without having to train a whole separate reward model and then run this complicated, clunky RL loop? Can we just cut out the middleman? And it turns out the answer is a big yes. And the solution is called direct preference optimization, or DPO. It is an incredibly elegant approach that completely bypasses the need for an explicit reward model and gets rid of that entire reinforcement learning stage, all while getting you to pretty much the same place. The magic behind DPO is a really clever bit of math. The core insight was realizing that the reward function we are trying to learn is mathematically tied to the policy we're trying to optimize. So, instead of explicitly training a reward model, DPO just rephrases the problem. If you look at the loss function, you'll see that the R for reward is gone. It's been replaced by this log probability ratio. All that is the probability of the winning answer under the new model versus the old one. We're directly telling the model, hey, make the good answers more probable and make the bad answers less probable compared to how you started. It's that direct. So yeah, the absolute key takeaway here is that the reward is now implicit. It's defined by that ratio of probabilities. And that one brilliant move collapses the entire complex RLHF pipeline into a single step. We're not doing this multi-stage dance anymore. We've basically transformed a difficult reinforcement learning problem into a much, much simpler classification problem. Just learn to classify which response is better. And this table really just lays it all out. Look at the difference. RLHF is this big three-stage process. DPO is just two. RLHF is complex and can be unstable. DPO is simple and robust. And maybe most importantly for anyone actually doing this stuff, RLHF requires you to juggle multiple huge models during training, while DPO is way more straightforward. It's simpler, more stable, and more efficient. It's a huge win. So what's the big picture here? The key takeaway is that the entire field of AI alignment is evolving, and it's moving fast. We're shifting away from these complex, multi-stage reinforcement learning pipelines and moving towards more direct, mathematically elegant, and stable methods. We're finding smarter, more efficient paths to teach these models what we actually want from them. And this simplification, this move towards methods like DPO, it really opens up the door for what's next. Because now that the process is more efficient and stable, we can start asking harder questions. The next frontier isn't just about making a model generally helpful. It's about how we capture the really subtle, nuanced, and sometimes even contradictory things that we humans value. How do we teach it not just to be correct, but to be creative, insightful, and truly trustworthy? That's the next big puzzle.